Hello, this is Doug Montgomery. I'd like to welcome you to our Fireside chat for the month of October. For those of you that are new to the Fireside chats and even to the Design of Experiments course on Coursera, I'd like to kind of go over a couple of things with you. This is a program that we do every month with a guest speaker, and the idea here is to explore some specific topics and maybe some applications and maybe even elaborate on some things that are only briefly mentioned in the course itself. We always have some time after our guest has presented their talk for some questions, and I hope you will take advantage of that. You can ask questions about either the Coursera course itself. You can ask questions about any specific sort of situation or application of experimental design that you're interested in. And of course, if our guest talks about something that sparks a question or some interest on your part, please feel free to ask a question about that situation as well. For those that are on Coursera, we post the recordings of these Fireside chats after they're completed, and you can find them in the resources tab of your course. And all of the Fireside chats that we have done up to now, and I think this is number 15, are all out there. And I encourage you to take a look at them because there's some really interesting, fascinating talks that have been given by our guests. Quick reminder about how we like to operate things. Please continue to keep your microphones muted, your cameras off during the session so that we don't have any background noise that would interfere with things. If you have a question for either me or our guest, please do submit that by using the chat function on the Zoom menu. And you don't need to wait until the Q&A session, part of our session, begins to do that. You can submit your question at any time during this hour that we're on. And if your question doesn't get answered during this time, we will figure out a way to respond to that and post that in Coursera for those that are enrolled. And you can always email me at my ASU email address with any questions as well. I'll be happy to try to address those. Our guest today is Dr. Maria Wiese, and she is an associate professor of business analytics at Miami University in Ohio, Oxford, Ohio. And her research covers a wide range of topics in experimental design, including screening experiments, analysis-based design methods, statistical process monitoring, and business applications of analytics. And she's very well published. She serves on the editorial board for both Quality Engineering and Quality and Reliability Engineering International. I'm one of the co-editors of Quality and Reliability Engineering International, and I rely on her a lot. She's an excellent reviewer, and I'm really pleased that she's going to talk today. She got her PhD in statistics from the University of Tennessee, and her undergraduate degree is in chemical engineering from Virginia Tech. She's another Hokie, just like me, except I'm a 3-time Hokie. And Maria, you're only once, right? That's all right, still counts. Okay, so Maria is going to talk today with us about a topic that is only really briefly mentioned in my textbook and in the course. And that's the idea of supersaturated designs. And so, Maria, I'll let you take over, and it's all yours.
Thank you. I really appreciate you inviting me to share some of my research and learnings from my research on supersaturated design. So I hope that you'll find this interesting. To begin, just to make sure that we're all on the same page, I do work at Miami University. And this is what a lot of people think of when they hear the term Miami University. But this is really what I see when I drive around Miami University. I am actually in Oxford, Ohio. I am not in Florida. And just a reminder that we were a university before Florida was a state. So today I'm going to talk to you about supersaturated designs and their use in screening experiments. And just to ground us all, as I'm sure that some of you are familiar with as you're working through your DOE course, like a typical screening experiment. So this is a typical screening design, a 2-level screening design. It is a Plackett-Berman design. And you would use this type of screening design if you were interested in studying the main effects from a system. The type of designs that I'm going to talk to you about today look a lot like those screening designs. We're still talking about 2-level screening designs, except that the number of experimental runs is less than the number of factors that you wish to study. So here's an example of a 6-run experimental design to study 9 factors. And the problem with this comes in that our typical least squares regression methods that you would use to, say, test all of the main effects at one time are no longer applicable. So today I want to talk to you about what we think are maybe some of the best practices with using these designs and give you some options based on the latest research on which type of supersaturated designs that you should consider using. Again, just as a background, I'm only considering today that we are interested in screening for just linear main effects. I included this terminology because you're going to see that X matrix notation later in the presentation when I'm describing the construction of some of these supersaturated designs. So one thing that we notice as researchers is there's actually quite a bit of research on supersaturated designs. And you Google Scholar search will turn up quite a few results. However, if you actually look for publications where someone has used a supersaturated design in a screening experiment, those are very rare. We have only found maybe 7 to 9 at this point of those types of experiments. So since I mentioned them, let me go through just a couple of examples of where these types of designs have been used. So here is a paper where the authors used a 12-run experimental 2-level design with 24 factors. And they actually used the design to design their sample composition for testing water samples. So that was an interesting use of the design matrix. Here's another example of a screening design. The authors in this used a 10-run screening design to study 17 factors influencing the extraction of gelatin from the skin of cuttlefish. I don't think I want to know much more about that. And they were able to successfully find which factors were most influential in this gelatin extraction. And lastly, here's a recent example where these authors use an 18-run design to study 31 factors and actually found 10 to be important. And after that, they projected those 10 onto those original 18 runs and were able to fit a linear model and further reduce to find the factors that they need to include in their follow-up experiment. Just to give you a little bit of idea of where these designs could be used, that should help you out. So our research questions when we started some of our projects are, why aren't people using supersaturated designs? And is there something that we could do as researchers to help people know that these are techniques that would be useful in screening? And can we make supersaturated designs more of a go-to in your screening toolkit? So the rest of my talk will follow follow this outlines. At first, we used our informal networks and reached out to people we know and asked some questions about what practitioners are using and what they're fearful of with supersaturated design. So we'll go through that. Then I have some excerpts from the literature, which might be enlightening as to why people maybe haven't adopted these types of designs. I'm going to discuss screening so that we can frame the situation where we would consider using one of these designs. And then I have two examples of recently published supersaturated designs and matching analysis methods that will be compared and contrasted. And lastly, I'll end with some practical advice for those of you considering these types of designs and talk briefly about what me and my co-authors are working on in terms of research. So first, let's talk about this informal survey. And it is informal. This was not random. We used LinkedIn groups. We used people that we know. We just reached out and decided to ask people a little bit about their experience and what they do in design. So all of the following results are based on just 63 survey responses. And the majority of people who responded to our survey work in engineering, manufacturing, and technology. The majority of them had graduate education or graduate degrees in statistics. And, they mostly use response surface methodology and fractional factorial designs, and then split plot designs are up there. Those are the top three on that left graph. And their most common method of analysis is regression or ANOVA, and that's not surprising because the typical response surface and fractional factorial and Plackett-Berman designs are designed to optimize the analysis by least squares, regression, and ANOVA. We did ask our users if they had any experience using supersaturated designs, and there were a few. So the first one was a failed experiment. And then we got a couple of responses. Someone used it in analytical method robustness testing. Someone used a supersaturated design to characterize drill bit effectiveness. And someone used a Bayesian d-optimal design and was apparently able to project that design down. So there are people using these designs in the wild. And then lastly, we asked them, if you're not using a supersaturated design, why is that the case? And the largest response we got was concerns with sparsity and power, and rightfully so, right? If you have less available experimental runs to analyze your factors, then you are not going to be able to complete a traditional least squares analysis. There is no free lunch, and in order to detect effects with these types of designs, you do have to have fairly large main effects. So power is definitely a concern. The second response on there was a little bit surprising to us. And, we sit in an ivory tower in academia, so we didn't really consider this, but a lot of times there is no reason to restrict your run size. So unless you have some sort of temporal or cost constraint, right? If your experimental runs just take a long time or have a lot of cost, then it's not necessary to constrain your run size. And then the third concern there was an uninformative analysis. And we took this as two ways, in that the analysis using this type of design can be uninformative. And then also there is no really agreed upon method in the literature on how to analyze these types of designs. So hopefully some of the suggestions that I'm going to give in this talk will definitely address some of those concerns, except the fact where they're not needed. So let's talk about what the research says about these supersaturated designs. So the first paper to introduce supersaturated designs was actually a paper by Swatherwright, I don't know if I said that correctly, in 1959, where he introduced random balance designs. And that paper was also published with many discussions. And John Tukey wrote one of those discussions. And this is a quote taken from his discussion. About 3 years later, a seminal paper in supersaturated designs was written. So this is Booth and Cox in 1962. And they wrote the paper on how to construct algorithmically supersaturated designs. And we're going to talk about this construction method later. And it's interesting because they go through the entire presentation. And then at the end, you know, they say, well, we don't know if these would ever actually be useful. This kind of contradiction continues later on into the literature as well. Giorgio wrote a great review of literature of supersaturated designs. And he was actually pretty cautious in recommending that people use these types of designs. But in another, this is a chapter in a screening book, Stephen Gilmore thought that in certain situations, these designs would be a good idea. So if practitioners are looking in the literature for recommendations regarding the use of supersaturated designs, they might actually get some conflicting advice. So let's talk about, before I introduce the two types of designs and analysis that I would recommend you use, let's just talk about factor screening in general. If we are screening for factors, and this is the case whether you're using a supersaturated design or a typical screening design, you are leaning heavily on the assumptions of effect sparsity and effect hierarchy. So effect sparsity says that the majority of your effects are going to turn out to be probably not as important as a few, right? So you can think of Pareto, the 80-20 rule, that you're going to be able to consider a few of the main effects to be really important. And notice I said main effects here because we also lean pretty heavily on effect hierarchy, in that we understand that interactions are often present in a system, but it generally follows that the size of the main effects are going to be larger than the size of the interactions. And these two principles have been verified empirically in the literature. So in this paper, these authors, they had over 100 published full factorial designs, and they went through and reanalyzed them and actually quantified the sparsity of the main effects and the two-factor interactions, and then also the hierarchy. And they found that, as the assumptions stated, that the main effects were about 2.5 times larger on median than the two-factor interactions, and that only a portion of the effects in the factorial experiments were actually found to be significant. So I think we can feel pretty good about leaning on these principles. So in traditional screening, we have constructed our designs, like that Plackett-Berman design or fractional factorial, to have good least squares estimation. And this happens when we have a small covariance matrix. So there's that X model matrix that I pointed out in the beginning of the presentation. And we can make this covariance matrix as small as possible by ensuring that our design has orthogonal columns. And that's typically what a screening experiment will do. But when we have less runs than we have columns, well, it becomes impossible to have orthogonal columns. And therefore, it becomes impossible to have such a small covariance matrix, not to mention the fact that it's not possible to estimate all of the main effects if you don't have enough degrees of freedom to estimate them. So is it reasonable to think, or is it a good strategy to consider minimizing this covariance matrix when you're thinking about constructing a supersaturated design? And we also assert that the goal of screening is not to make precise estimates, right? The screening experiment is always your first experiment, and it's always going to require some sort of follow-up. And the goal of screening is to identify important factors. So for example, let's say that we have these 5 factors with these true coefficients. So the first 3 are active, the last 2 are not. We might run a penalized regression estimator, and we may get some biased estimates. And it turns out here that our estimation is really poor, but our screening results would be perfect. And this is something that we assert that if you're going to use a supersaturated design, that you really have to keep in mind what the goal of screening is. So if we're thinking in those terms, then we assert, me and my colleagues, that a good screening experiment is going to have high power, right? We're going to be able to identify the important effects, not necessarily give them good estimates. And, we might be okay accepting a little bit more of a type 1 error at the, given that we can have more power. And this is a trade-off that an experimenter should be able to make. And the two methods that I'm going to present to you today, actually, one will give this increased type 1 error and the other will not. And so what we assert is that supersaturated designs should actually be constructed to enhance factor identification and not factor estimation. In traditional supersaturated designs, they actually have been constructed kind of emulating a orthogonal design. And this emulation is kind of insinuating that you're trying to optimize factor estimation. So that Booth and Cox paper that I discussed earlier introduced this, what we call the ES squared criterion. So there's that X matrix that I pointed out, which in our case is just the design matrix and an intercept column. And what the ES squared criterion tries to do is make the off-diagonal elements of that information matrix there as small as possible. So effectively trying to emulate orthogonality. And so we're trying to approximate that ideal structure as close as possible. But as I just stated, is this the best course of action when your degrees of freedom are not even, you don't have enough degrees of freedom to fit that least squares model? So let's talk about different ways we could construct supersaturated designs for screening, and two particular construction methods that are paired with analysis methods that will allow us to obtain our goal of screening, which is actually to identify important effects, not necessarily give them good estimates. So the first one on the left here is a recent paper introducing, the acronym is GO SSD, but Group Orthogonal Supersaturated Designs. And the paper on the right, my right, is a 2017 paper of mine and my co-authors with introducing algorithmically constructed supersaturated designs that are best when analyzed with the Danzig selector. So let's look at these two different supersaturated design types. So these group orthogonal supersaturated designs have a very unique structure. On the correlation plot you hear, this is a correlation plot of the columns of a 20 run and 24 factor GO SSD. And you notice immediately this very unique block diagonal structure. So the groups in a GO SSD are actually orthogonal from one another. So within each group are the factors, and the groups are orthogonal to one another. Not shown here, but there's an extra group included in these designs with what the authors describe as fake factor columns. And these fake factor columns allow the user to make an estimate of the experimental error. The nice thing about these designs is that they're very easily constructed using a couple Hadamard matrices. You could do it very quickly in R. The drawback is, though, because of their special group structure, there are some run and factor size combinations that won't work. The analysis method for these designs, and I'm just going through a really high level overview. I'll give you some information of where to find these designs and these methods later. But it's kind of a standard group screening type of analysis. So first we're going to pick out the groups that are important. And then after that, we're going to include the factors in those groups in our second analysis. So in our group testing stage, we're going to use that estimate for sigma squared And we're going to test the groups, pulling the degrees of freedom for any non-significant groups as we go. In the second stage of factor testing, we're going to take all the factors that in the groups that were identified, and we're going to do kind of a best subsets or all possible models. So we're going to start with all models of size 1, and we're going to collect the significant F tests. Then we're going to go to all models of size 2, and we're going to repeat that up to a model of a certain size. And the size that me and my co-authors recommend is about, it ends up being about half of the factors in the group, or the rank of the group over 2. And if all of the models up to that size, up to that certain size, are significant, then we're going to classify all of those factors as potentially active. And so that is called the fit-go SSD analysis. Here is a picture of the second type of supersaturated design, and this is a much different looking correlation color plot. So this again is a 20-run supersaturated design to study 24 factors. You'll notice there is no group structure in this design. And the way that this design is constructed is algorithmically. So in the ES squared criterion, so UES squared is unbalanced ES squared. That's a generalization of the ES squared criterion that I talked about from Booth and Cox. Their goal was to make the off diagonals as small as possible. Our goal is to minimize the variance of the off diagonals. So we want to make them the same as possible. And if you just did this alone, well, it's not a very good criterion, because you end up with a design that has all the same columns. So we had to add a couple of different constraints. The first constraint is a ES squared or UAS squared efficiency, and that keeps us from ending up with all the same columns. And then the second constraint there, you see that UES squared greater than 0. We force the off diagonal elements of that information matrix to be positive on average. So if you look at that correlation color plot there, hopefully you'll notice that it's rather blue, and that most of those off diagonal elements tend to be positive. And here's what we found. We found that when you construct a supersaturated design like this, and you were able to specify your effect directions in advance. So what does that mean? That means I think factor A is going to have a positive effect on the response. So I'm going to assume that its estimate's going to be positive. Factor B has a negative effect on the response. I'm going to flip the signs in that column, and then therefore I can make that positive. And what we found is, if you can do this, that our supersaturated designs have higher power, and this higher power comes with not elevated type 1 error. And that's compared to that traditional constructed supersaturated designs, that UES squared design, the ES squared that we talked about, or Bayesian de-optimal. And this effect was particularly pronounced when we used the Danzig selector to analyze these designs. The good thing about this is, even if you incorrectly specify all of your effect directions, the performance of these designs with the Danzig selector is no different than the traditional supersaturated design. So you really kind of have nothing to lose by guessing the effect directions. And just to mention, Go SSDs also benefit from specifying effect directions in advance. That's almost sort of a Bayesian type of thing, right? We are providing more information into our analysis, and therefore we do a little bit better. One thing I do want to mention, just in case you're not familiar with the Danzig selector, it's similar to the lasso, if that's something that you are familiar with. It is a penalized regression method, and the way that these methods work, the Danzig selector actually solves a linear program for many, many values of that delta. And as that delta increases, the coefficients actually shrink towards 0. And even though you'll see in the research that the Danzig selector is implemented in an automatic procedure, we do not suggest that you analyze these designs with any sort of automatic procedure. The nice thing about these regularization methods is that you're able to plot the values of the coefficients as that constraint increases, So you get a nice profile plot, and this would be the analysis of that VAR-S plus design. So here is an example of a profile plot where it's very obvious which factors are driving the system. And just to make sure I'm not painting a very rosy picture, here's a picture of an analysis of a supersaturated design where the results are a bit ambiguous. Like, it would be a little bit harder to decide here maybe which factors you'd like to continue on with. So I didn't go into a bunch of the research and the nitty-gritty comparisons. I'm just going to go through the conclusions here. If you are interested in conservative screening, right, that you want to be careful not to eliminate too many factors, then the GoSSD plus the GoSSD analysis is going to be your choice. We have found that the GoSSD analysis is going to provide you with information on the sparsity of your true system, in that your models are actually going to get large linearly as your sparsity is decreased in your true system. They're very easy to construct. The drawback is that there are some design or run and factor sizes that aren't available. And I didn't include these results, but I did want to mention them. In our paper, we simulated a situation where we had interactions present in the true model, but you weren't screening for them. So kind of like a nuisance interaction. They're out there, you don't know they're there, but you're screening for main effects. And what we found that the GoSSD plus that specific analysis was a little bit less robust when those interactions were present than compared to the VAR-S plus designs and the Danzig selector. So that combination of supersaturated design and analysis is going to be a more aggressive screening. So you're going to produce generally smaller models. They're algorithmically constructed. So any design run and design size combination is available. And we did find that if you are screening and there is an interaction present in your system, these supersaturated designs are a little bit more robust. And by robust, I mean robust in terms of power and type 1 error and general performance. So let me give you just a few slides on some practical advice if any of you are considering using these designs in practice. I didn't mention it, but there has been research on, how big of a design or small of a design can I make? There is no free lunch, and there are some limitations that we should mention. It's generally agreed upon that you should expect to find about n/3 active effects from a supersaturated design. So when you are considering the number of factors to study and your run size, you should really consider that sparsity level. After that, it just becomes hard to detect these effects. Also, you shouldn't get too crazy when designing your supersaturated designs. Try to keep your number of factors no more than 2 times your number of runs. Again, after that, the power and the type 1 error suffer. If you are interested in obtaining VAR-S optimal supersaturated designs and code to run the Danzig selector, if you use this, look up this paper, there's supplementary materials posted. There's a complete catalog of these designs, as well as Danzig selector R code. The Danzig selector is widely available in point-and-click software too, such as JMP. If you're interested in using GoSSDs and you use JMP, then you are in luck because those are already available in JMP software. And here's a picture of, you'll see the group orthogonal supersaturated designs and the fit group orthogonal, that particular method that I discussed. So just a summary of some of the practical advice. So keep your runs to factors reasonable, plan for the number of active effects to be sparse, go ahead and specify your effect directions ahead of time. It won't hurt. For aggressive screening, use the VAR-S optimal and the Danzig selector with a profile plot. For conservative screening, so larger models, use a GoSSD and JMP and analyze with the fit group orthogonal method. And you are going to need to follow up these experiments. And that is definitely a hole in the literature right now. But there was a paper by Gutman who suggested a Bayesian de-optimality follow-up approach. And as far as me and my colleagues could tell, that's probably your best bet. One more slide, just what we're working on now in terms of these designs. So we are still thinking about good, smart ways to follow up a supersaturated design. There's a lot of people kind of thinking about what if you do want to screen for interactions at higher order terms using a supersaturated design. And currently right now, the work that is in progress is we are looking at exploiting properties of regularization methods to construct supersaturated designs in the same manner that folks have exploited properties of least squares to construct other screening designs. So thank you, Doug, for listening. If anyone wishes to contact me or ask me questions or would like resources, please feel free. Here's my contact information. And here are some references that I mentioned in the paper.
Great. Maria, thank you. This was really a very informative talk. And I do have a couple of things that I want to talk about with you. And one of them is kind of an alternative to SSDs. And it's particularly nice if you know or have a pretty good idea of what the effect directions are, and that's the idea of group screening. And I wondered, what you think about that. If you know the effect directions, and there's some logical way to group the factors together, group screening could really work quite nicely. And I just wondered if you have any experience with that or any thoughts about that.
It seems in the literature that group screening is very much a two-camp issue. You're either for it or you're against it. I have seen it compared to, there was a 2014 technometrics paper. Angela Dean was on it, as well as there was a graduate student at the time. I can't remember his name. And they compared traditional supersaturated designs as well as group screening methods. And what they found is that the group, and this was in a massive simulation study, and what they found that the group screening methods just weren't as effective. But I do think that the Go SSDs maybe are a marriage between traditional group screening and the maybe more algorithmically constructed supersaturated designs, because they do mention in their paper that if you can guess effect directions and put those positive factors or negative factors all in one group, that would be beneficial. And so I personally haven't done any simulations with group screening, but I know that is definitely an option. And we very much borrow or justify our suggestion for trying to attempt to guess the effect directions ahead of time from that research.
I've personally only had one experience with group screening, and it was a long time ago. It was back in either the late 70s or early 1980s, when I was still a faculty member at Georgia Tech. And at the time, I had a research contract with the Office of Naval Research. And it was a wonderful research contract because they let me do whatever I wanted to do. And the only fly in the ointment is that I was sort of on call to be the Navy's consultant on interesting, and by interesting, I mean ugly problems that showed up. And so there was this one ugly problem that showed up. There were some people developing and trying to implement a large-scale computer simulation model of tactics for an aircraft carrier battle group. And what they were interested in is what sort of tactics would be effective in preventing a submarine attack or an attack by land-based aircraft. And of course, they were worried about the Soviet Union because they were the only people that had significant submarine capability back in those days. And they didn't really know how to operate aircraft carriers. So all of their aerial forces were land-based. And so they had this big simulation model, and there were lots of factors because you have something like 20 vessels in this group. You have the carrier, and then you have the escort vessels, destroyers, cruisers, anti-submarine warfare, destroyers, and so other support vessels. And they all have speeds, they have headings, they have tactical maneuvering rules that you would follow in the event of an attack. And they wanted to figure out, okay, given a particular type of attack scenario, what are the right values for all of these factors? And so they had this massive computer simulation that ran forever. Okay, if you configured this thing and ran it, for one run of the simulation, it would take forever, literally hours. And they not only wanted to use it to learn about tactics, but the idea that they would also use it to train the operators in command of the carrier task force, so that they would have some idea, how to react to changes in the attack scenario they're confronting. Well, it turns out you can group a lot of these factors together. Like you can put all of the headings for the escort vessels in one group, and you can sort of guess the direction of the effect.
Mm-hmm.
And so we what I ended up doing was taking some, I don't know, 30 some factors, some massive number of factors, and putting them together in something like about 6 groups, and then running a group screening experiment. And it was pretty successful in that we were able to boil it down after a lot of analysis. We were able to boil this thing down to something like less than a dozen factors that you really needed to worry about.
Yeah.
And so I thought it was pretty successful.
Yeah, that is successful.
But looking back on it, it's also probably a scenario where a supersaturated design would have also been a very good choice, because you were looking for large effects. You weren't necessarily worried too much about interaction effects, just because of the nature of the problem, and you wouldn't expect a very large number of the factors to be active. And it turns out like less than a third of them basically in that experiment were active. So I kind of wonder if maybe that question, because I'm familiar with the paper that you cite, that did that comparison between group screening and SSDs. I just wonder if some of that needs to be revisited and thought about in maybe some more detail, because group screening would to me seem to be a viable alternative, at least in some cases.
Yeah, and I think because we have, I don't want to say better, new and different analysis methods available to us that you didn't have, right? We have lasso, we have group lasso,
right? Danzig selector.
Danzig selector. We have all different versions of the group lasso, and I'm not sure how much of that, how, if any, development has happened in group screening with thinking about these newer types of methods.
I was doing this in an era where we didn't really know much about these generalized regression methods, and I just relied on good old ordinary least squares to analyze the data, and then looked at the results and spent a lot of time talking to the Navy people that were developing the simulator, and a lot of time talking to people that were actual fleet officers that could help interpret the results. But I think there's a whole array of things that could be looked at in the context of comparing these different methods. And I just think that's an interesting research question that maybe it would be worth exploring.
Yeah, for sure. There's a lot out there. And in terms of, there's a couple people now working on a problem that similar, right? That unfortunately the regularization methods aren't as neat to work with in terms of their mathematical properties as these squares. And you get pretty blindsided pretty quickly. And I'm assuming that's why it hasn't been done. So there's another group working kind of in, not, I don't want to say competition with us, but looking at how can we make that design matrix to actually exploit some of the properties like the strong irrepresentable condition and some of these regularization methods. It's not easy. And so I know why it hasn't been done yet.
Well, just the interpretation of something like Danzig is tricky, because you showed that plot of how the coefficients are shrinking as a function of the tuning parameter, and it's clear that there's not an obvious answer.
Sometimes there's not. And I think when you use a supersaturated design, you have to be a little bit willing to deal with not an obvious answer.
Yes. But again, that's the whole idea of screening, is to get some ideas about what might be important.
Exactly.
I have a former doctoral student who you may know or may know who she is, Carly Metcalf. She teaches at RIT now, and she was actually a guest on one of the early Fireside chats. And her dissertation work was on the analysis of non-regular fractional factorial designs. And she looked at Danzig selector very thoroughly in her dissertation, and found that there are some difficulties in interpretation, but it doesn't do badly. And it works better than a lot of other things. But then she developed a technique that we call AIMS, the alias informed model selection. Method. And it works much better than Danzig. And but it takes advantage of the fact that something about the alias structure of the effects. And she was focusing on main effects and two-factor interactions, and found that for the designs that she looked at, that these methods work. This AIMS method works really, really well. In fact, there's a paper coming out in Quality and Reliability Engineering International this next month that describes the AIMS method and shows how it's applied to one case. But that's another sort of technique that maybe something like that could be developed for SSDs. I don't know. That's just a kind of a throwing out an idea, because I think these designs have enormous potential. Enormous potential. I remember years ago in a consulting project, I was confronted by a problem that had something like 9 factors. Okay, and every run of that experiment cost $100,000.
Geez.
$100,000. And your traditional 16 run fractional factorial is not going to make people happy. And we ended up using a 12 run Plackett Berman design, and it worked. The problem got solved, but it was still way over $1 million in cost. And I think that's a classic situation where SSDs make a lot of sense.
Yeah, I know of another example from the Lubrizol Corporation. They do oils, engine oils, and they were doing engine testing, which is very expensive, very long, very tedious. And they have a published paper, I think in Quality Engineering, kind of outlining their strategy for using supersaturated design for some of that.
Right. And you very frequently run into situations where you just don't want to do a lot of runs, even if it's not a cost related issue. I mean, one of the things that I've learned over the years in helping people design many real experiments is the more runs you have in the experimental design, the more likely it is that things go wrong. And people, something happens. The factors don't get set correctly. Some hideous mistake is made in measuring the response. And so trying to keep the number of runs reasonably small is important. And if you have a lot of factors, that's hard to do. That's just hard to do.
Yeah.
So I think these things have great potential. And I wish I had spent more time dealing with this in the last edition of my textbook, but I was just so pressed to get the thing out that was one of the topics that I wrote myself a post-it note and said, okay, edition 11, this is something we're going to do. We're going to talk more about SSDs, and I'll probably ask you for some advice about what to put in there when the time comes. But I really appreciate this talk. And the other thing I want to compliment you on in the talk is your discussion of type 1 error, because people get too excited about type 1 error control in screening designs. Mm-hmm. And frankly, in a screening design, what kills you is a type 2 error.
Right.
Yeah. As soon as you figure out something's not important, you never think about it again. But a type 1 error, if it's not important, you'll figure that out.
Exactly.
Yeah. And people get all wrapped up about type 1 error rate, and I don't even think of it as much of a problem in screening designs.
No, I mean, it just really is, it's all about your threshold. It's kind of how stringent you would like to be and how many factors you screen out.
Right. And you're typically looking for large effects,
right?
2-3 standard deviations. If the effect size isn't at least 2 standard deviations, it doesn't really have much impact on the system.
Right.
So like I say, people think too much about type 1 error, and I'm glad you brought that up because that's a really important point.
Thank you.
So we have one question that has showed up. Can you see the question, Maria?
Yeah, I can see it.
Okay, well, let me read it because I don't think our audience will be able to see it directly, but here's the question. It says, when developing a process, we perform 20 large-scale batches, and based on which lower and upper limits were set. Okay, and we'll come back to that statement in a minute because I'm not sure what kind of limits we're talking about at this point. After that, commercial batches have been continuously executed. We are generating data almost daily. Now we have 150 batches of data. Recently, we introduced a change for which comparability or equivalence has to be demonstrated. Now that we have more data, should we revise the upper and lower limits set earlier? If yes, how many more batches should be used for revising limits? It's not desirable to use 150 new plus 20 batches for setting new specs. Okay, so now I go back to that first sentence. Were they talking about specification limits or control limits? Not clear. But to me, this is the kind of problem that really control charting methods need to be applied to. Would you agree?
Oh, yeah, absolutely. That's the first thing I thought was, that a control chart of all the batches would tell you, they said they have a change. It will tell you where the change occurred.
Sure. And how big.
Right. And it might tell you the number of batches you would need to use because you mark that change point in time and go from there. Right.
The 20 initial batches should be adequate to establish what I would call trial control limits.
Right.
And if everything is in control, then you extend that forward and you plot the data from the new 150 batches on that chart. And if things remain in control, then life is good.
Right.
But then you make the change and you can see the point in time where you made the change on the control chart. And you can see if anything happens. Did that change result in points being out of control or some indication of a process change, like suddenly now points are all plotting above the center line on the chart, something like that.
Right.
And again, if you're going to have to reestablish new control limits,
20 current batches should be plenty to do that. I don't think that would be a problem. Now, if they're talking about spec limits, we have a different problem because control limits have nothing to do with spec limits. Spec limits are driven by either what you want to do with the material or what the customer wants to do. It has nothing to do with statistical control.
Right.
So they need to decide, what are they really looking for? Are they looking for stability in the process, which is statistical control, or are they looking for some way to set spec limits? And
Right.
is that kind of your thinking on this?
Yeah, I was reading it and thinking control charting until the last sentence.
Yes.
And I might be overreaching here, but I'm wondering if they are confusing the two sets of limits, as that is not uncommon for that's not an uncommon mistake to
That
make.
happens a lot.
Mhm.
I can remember going through a plant that was making power supplies for personal computers, and I saw these limit lines on the control chart, and they looked kind of funny. And I said, "Where did you get these from?" They said, "Oh, these are the spec limits." So they were plotting spec limits on a control chart, which, you know, just makes no sense whatsoever.
No.
And what I would do is I would encourage these people to approach this problem using control charts.
Yes.
Does that seem reasonable advice to you?
Yeah, I think so. I think they'll be able to answer all of their questions.
Sure. And the specs can come from some other place.
Right.
It depends on what either you want to do with it or what the customer wants to do with it. So that was our last question. We only had one today. Maria, I want to thank you for a great talk. I thought this was super informative. And I'm glad you sent me a copy of the slides, because I'm not going to keep those and refer to those myself. We are going to do a fireside chat in November. It's scheduled for Wednesday, November 10, same time. And my guest is going to be Julia O'Neill from Moderna, and a company that's been involved in the vaccine business.
Mhm.
And more information about Julia's talk will be forthcoming. And again, I thank all of you that have expressed some interest in our fireside chats. And once again, Maria, I want to thank you a lot for a really great, really informative talk.
Well, thank you. It was fun sharing this information, and I really appreciate you thinking of me.
Not a problem. Thank you very much.